So when these handouts become available, you'll be reminded to come and pick them up just like you did today. Or it might be the case that I'll ask you to download them from the Absolutely Chemistry webpage, or perhaps the Sakai website. Either one, doesn't make any difference. I will tell you which website such information is posted on if I ask you to download it. And Absolutely Chemistry is now active for this term. Our last class gathering was captured and is posted. In order to distinguish the lectures for this term relative to last term, where last term's lectures started with 01, this term's lectures start with 001. And you'll follow subsequent lectures like today, following in numerical sequence after 001. Now, Wikispaces, which is what I use for Absolutely Chemistry, has some interesting ways to pay attention to numerical order. So I don't know if today's lecture will be 0010, 0011, or 002. But you'll find it after I see which number system Wikispaces likes. And then I'll use that number system. But the lectures also be posted by date. And they'll always be on the first page after I get into the body proper of the entire menu of all the lectures that are contained on Absolutely Chemistry, which is now 5 pages worth. I'll always post the lectures corresponding to our present lecture gathering starting on page 1. You won't have any trouble finding it. Use it as necessary. It's there for you. And now, the last part of chapter 17, which is really an aim to get you to realize how, in many cases, you will have to solve problems from a number analysis standpoint. How to do the calculation. We were looking at this equilibrium system. We arbitrarily assigned to it the simplest possible equilibrium constant value of 1.0, a constant represented or given to 2 sig figs. We started with this system of nitrogen, hydrogen, ammonia gas mixture in a 1.0 liter internal volume piston cylinder gadget. And since the system was originally containing 1.0 moles of each gas with this equilibrium constant, we see the system originally was at equilibrium. But then we applied a change. The change we applied was to reduce the volume by increasing the pressure until the volume was divided in 2 and now became 0.50 liters, at which point we locked the piston in place. So at the instant at which we made the change, did the equilibrium exist? At the instant at which we made the change. No, we killed the equilibrium. Now, textbooks have a nasty habit of talking about equilibria which shift. I don't like that language. No respectable equilibrium will ever shift. It's the most stable thermodynamic state a system can exist in. Why in the hell should it shift? What they fail to point out is when you applied this change, in our case, we reduced the volume. We could have destroyed the equilibrium by increasing the volume. We could have destroyed the equilibrium by adding additional quantity of any individual component of the system. We could have destroyed the equilibrium by adding or taking away a quantity of any of the original components, or 2 of the 3 original components, or adding 2 of the 3 original components, or adding all 3 of the original components, but not in the correct ratio to maintain equilibrium. There's an infinite number of ways to wipe out this equilibrium. But what does Le Chatelier's principle tell us? Did you read about Le Chatelier's principle in chapter 17? A simple, brilliant statement made by famous French chemist Le Chatelier, I don't remember his first name, so what? He recognized that since the equilibrium state is the most stable state, thermodynamically speaking, that a reaction system can exist in, if you do something to an equilibrium system which disrupts the equilibrium, that system will if at all possible react to do what? Get back to equilibrium. You're damn right. So, in this case, the change we applied, as we've already noted, disrupted the equilibrium, and we also noticed that the internal reaction, the system reaction, which must take place to get us back to equilibrium, is for this system to react this way. Now remember, this is an equilibrium system. I don't have to take the equilibrium constant and invert it just because the reaction goes this way. All I have to do is pay attention to the directionality of the reaction that takes place in the system to get us back to equilibrium, and do my algebra accordingly. Now then, another consideration which we didn't make last time but we'll make mention of now, that we could have used to recognize that the reaction which must take place to get us back to equilibrium is the fancy Q consideration. Fancy Q is known as the reaction quotient. How do we write fancy Q? It's just like the equilibrium constant. Exactly the same as the equilibrium constant in appearance. What's the difference between Q and K? K means we're at equilibrium. Q means we're under any imaginable set of conditions, of which equilibrium is only one possibility. But of course, if we're at equilibrium, then Q is equal to K. Nothing fancy about that. But under any other set of conditions, Q is not equal to K. Q is either going to be bigger than K or smaller than K. If Q is bigger than K, which direction must the system behave to get back to equilibrium? Right to left or left to right? Right to left. But if Q is smaller than K, then in order to get a value that rises up to become as large as K, means we got to have the reaction proceed in the direction for which the equation is written, left to right. Nothing fancy about this. So based on the change we applied to this system, initially, we still had a mole of each system component, but now, after applying the change, each mole of system component is living in a volume of 0.5 liters. So we go back to the equilibrium constant, which we've written in terms of molar concentrations, and recognize that the molarity of each system component is now 2 moles per liter. So here's Q. Well, that's tough arithmetic. Gives a value of 4, and 4 is bigger than 1.0. That means this thing has got to go right to left to get us back to equilibrium. Now, we wrestled with the algebra that relates to this change last time, and algebraically recognized that if we let the equation for the equilibrium reaction be our algebra guide, which you should do always, and using the most famous representation for an unknown quantity, at least as I believe it is the case in all algebra classes. What is this most famous representation for unknown quantities you find in algebra class? X. Does it have to be X? Hell no. It could be Y, Z, A, Q. Q squared over 25 pi to the 13th factorial. Boy, oh boy, oh boy. You want to use that for X? Not if you're sane. I'll tell you a story. You know, I like to tell stories. High school. Toledo Waite, where I went. My first year algebra class. 1956. Haha, where were you? Fall of 1956. My algebra teacher, I thought, was a very good teacher. Her name was Baumgartner. I don't remember her first name, Miss Baumgartner. She read about something, I think, in a journal about how people react when they see something they don't know. So she wanted to do a test, because I don't think she believed this. So she gave our class an algebra quiz where all the unknowns, just like in the textbook, were represented by X and Y. She gave the next class, which until that point in the term had been doing better than we were, on an average for the class basis, okay? She gave them exactly the same test with one change. Every X term was now A and every Y term was now B. So all the unknowns were A and B instead of X and Y. She was aghast to discover that they flunked. They flunked. And she asked this, what went wrong? And almost to the student they said, Ms. Baumgartner, we know about X and Y, but what's A and B? You see how people behave when they see something they haven't seen before? It's a normal human reaction. You remember 2045 when you looked at Planck's equation, E equals H nu? Looked like a strange equation, didn't it? But yet that equation is simpler than the equation for density. And I know you're all familiar with density. Use density arithmetic in the first lab assignment for 45L. D density is mass per volume for the substance in question. That's got three possible unknowns. But in Planck's equation, H is a constant, the Planck constant. So there's only two unknowns. That's a simpler equation. And now what you did yesterday in discussion class asked you to pay attention to another variation of density. You remember what that variation is? You heard about it yesterday. What is it? Charge density. Remember that? You hear about charge density yesterday? Didn't hear about charge density yesterday. Uh-oh. I'll have to have a talk with my discussion people. Well, then I'll tell you about charge density and show you how it relates to what we are presently doing. Don't try to hurry up and write it down. It's in the notes. D symbol is mass density, right? Mass of the substance per unit volume. Charge density is charge on the substance, or species I should say. And you could say per unit volume, but atoms in the main interact with other atoms by using valence electrons, outer electrons. So I think charge density is more a surface concentration than it is a volume concentration. So I think if we're going to calculate charge densities, we take charge on a species, like aluminum ion plus 3, divided by its surface area. That'll give you charge density for aluminum ion. How does charge density for aluminum ion compare to charge density for sodium ion? Which ion has by far the greater charge density? Aluminum ion. Because it's 3 times as plus and Al plus 3 versus Na plus. You recognize these species are isoelectronic? Remember what that means? They have the same valence electron configuration. With what noble gas atom are they isoelectronic? Their nearest neighbor, noble gas neon. I like the way that rolls along. Which is smaller than Na plus Al plus 3 or Ne. Which of these 3 species is the smallest? Which one? Al plus 3. Do you believe that statement? Why do you believe that? Hey, they got all the same valence electron configuration, don't they? They're isoelectronic. But that aluminum ion's got 13 protons pulling on that configuration, is going to pull it in more tightly. How about that? Okay? What's that mean? That means if I put aluminum ion in water solution, This aluminum ion with this high positive charge density exerts a natural Coulombic attraction on the non-bonding electron pairs of a water molecule. Because the non-bonding electron pair situated on the oxygen atom of the water molecule corresponds to the partially negative region of that molecule, right? You learned about dipole considerations in 2045, and the water molecule is dipolar. It's a dipole. The hydrogen atom ends are partially plus, the oxygen atom end is partially minus. Well, Coulomb's law, the most fundamentally important law in chemistry, at least that's my statement, because these chemical particles are fundamentally composed of protons and electrons, neglecting neutrons because neutrons in most cases don't have much effect on chemical properties. There's exceptions to that. Let's not worry about the exceptions. So, aluminum plus 3, because it's plus, exerts a strong attraction on this, the squiggle minus part of the oxygen atom in the water molecule. Ain't that right, Coulomb? Plus and minus attract, particularly strongly if these plus and minuses are concentrated pluses and minuses. And these are small particles, particularly aluminum plus 3. Consequence, water molecules stick strongly to aluminum plus 3. And in so doing, form a well-defined hydrated metal ion of aluminum ion. There it is. Why did I reverse the formula for the water molecule in this formula? Because the bonding is between the oxygen atom end of the water molecule and aluminum ion, isn't it? And I want to write formulas as best as I can to keep with structure. And the hell with textbooks who don't have enough sense to do this. If I tell you to write me a Lewis structure for the sulfuric acid molecule, and you use the formula H2SO4, are you going to glue hydrogen to sulfur? Probably based on the formula H2SO4. But if you glue hydrogen to sulfur, you're wrong. Some of my colleagues who do 2045, they said, oh, they know this. I said, like hell they do. You go ahead and after you talked about Lewis structures and ask them to write you a Lewis structure for the sulfuric acid molecule. Guess what they found out? Everybody got it wrong. I see, tell you. Our job is to communicate. And if you use these stupid formulas like H2SO4, which belies structure, you're inviting disaster. And you're doing a bad job teaching. See how friendly I am when I talk to people who don't do this right? I mean it. I'm serious about this. This is important stuff. And if we don't succeed in communicating, how the hell can you possibly understand what we're talking about? That's today's sermon so far. Maybe I'll pick it up with further. On we go. We'll have more to say about that ion and its chemistry next class. Now then, we talked about Q, and by looking at this from a simple arithmetic analysis standpoint, realizing that concentrations can never be zero or negative, we know that the value for x in this, the smallest term in this expression, has got to be less than 0.34, but bigger than 0.0, because if x is 0.0, then we get the Q value, and Q ain't equilibrium, is it? So, how do we solve? Because if you do this by rigorous algebra, you're in for one large headache. But if you solve it by common sense, it's easy. And that's the way we want it to be, as easy as possible. So we're going to use some arithmetic horse sense, which I refer to in the notes by the fancy term speculation method. I know the value for x is in between 0.33 or is less than 0.34 but larger than 0. Now, from a statistical standpoint, the value I should try first is the value that's halfway between those numbers. We'll talk further about that later. But instead, I'm going to pick a value which is as numerically simple as I can conceive. And that's 0.10. Because if I put 0.10 in as the value for x, it's easy for me to evaluate these terms. 2.0 minus 2x becomes 1.8, 2.0 minus 6x becomes 1.4, and 2.0 plus 4x becomes 2.4. So I'll put those values in, evaluate, and I get 0.86. 0.86 is a little bit smaller than 1.0. But it's kind of close. So I know my value of 0.86 for x isn't quite right, but it's pretty close to the true value. So I ask the question, is the true value for x somewhat bigger than 0.10 or somewhat smaller than 0.10? Because we've just found out that 0.10 isn't the true value for x, but it's close. What should I try now? A little bit smaller, because this relationship tells me as x gets bigger, what happens to this term? This term gets smaller. And I've already got a value that's too small. But as x gets smaller, this term gets bigger. Ain't that right? Because when x is 0, this term is 4. And that's too big. Ha ha. What are we doing? We're doing something I bet you haven't done before, but you should do. You're letting that expression talk to you. You're letting it tell you what it means from an arithmetic, horse sense standpoint. How about that? So, I now want to try a value for x that's close to 0.10 but a little bit smaller. Any suggestions? I could try 0.08. If I try 0.08, then I'm going to give it a value for this term when I evaluate it that's bigger than 1.0. So, you got the idea of how to play the game. I'm going to tell you to try this. Okay? That's 10% smaller than the first test value we tried for x. And originally we tried x equals 0.10. That's what we got. We see that's pretty close, but we know a value for x that's still a little bit smaller than 0.10. So I'm going to tell you to try this. If you try this, here's what you're going to get for this term right here. Because you know when you got the right value for x, and you substitute it in here, you get the values, you do the arithmetic, this term times this term cubed divided by this term squared. When you got the right value for x, what value are you going to get for this term? You're going to get 1.0, aren't you? Well, when I try 0.90, I get 1.017. Now, you may well at a glance look at this and say, hey, you wrote 4 significant figures. That's not correct, because I only got 2 sig figs allowed here with the data, and if I write this as 2 sig figs, it's 1.0. I got the answer. Or do I? Because this is ever so slightly bigger than 1.0 if I cheat on significant figures. Why am I cheating on significant figures? Because I want to be sure that I get the right value for x. Well now, this, just a little bit bigger. So I'm going to add to this try of x at 0.090. I'm going to try 0.091. Okay? I'm telling you the numbers to try. And once you know the numbers to try, to play the arithmetic with the pocket calculator is easy. The 4 significant figures, the test of x at 0.091 is 0.9999 for this term. Ha ha ha! That's also 1.0 when I write it to 2 sig figs. Which is correct? This or this? Which of these values is closer to 1.0 if I take it that after 1.0 I never have nothing but a bunch of following zeros? Which of those is closer to 1.0? Which is it? Sounds like we got some argument here. We have a hung jury. How many vote for 1.017? Then I guess we don't have a hung jury, because 0.9999 is correct. All you got to do is to take the difference of 1.0 and 1.017 and compare it to the difference of 1.0 and 0.9999, for which the difference is 0.0001. But for the first value, the difference is 0.017. And that's 17 times bigger than 0.0001. So now you know how to play the game. It's not difficult at all. And we're going to tackle many problems this term which have to be approached in this fashion. Unless you like to do great reams of arithmetic supported with powerful computers while exhausting many pencil points and large quantities of scratch paper and still not have the damn answer. You don't want to do that. Okay. Now, PSIs. We're in chapter 18. The foundation for which was established with what you did yesterday in discussion class. Remember what I said. Discussion class gatherings for this 2046 class are an integral component of the class itself. You miss discussion class, it's just like missing lecture class. Don't do that. PSI. If in a system a reaction occurs, the simplest and best way to express the chemistry shown by the reaction is to do what? A reaction occurs in a system. How would you like to report your account of this reaction? Write an equation for it. And the only equation we will accept is the correct equation. And you can't write a correct equation for a reaction unless you know what's in the system. How about that? Pretty obvious, isn't it? Yet the textbooks don't realize this. And I say again, that's just one more statement on my part why I don't use those damn books. And what you learned yesterday was what you have to consider to write PSIs for systems of Bronsted-Lowry acids and bases. Now, there are really only three types of systems which we will consider. Well, actually 4 types. Pure substances. Writing PSI for a pure substance is the simplest possible PSI because it's the pure substance itself. If you're dealing with pure hydrogen chloride, it's hydrogen chloride. If you're dealing with pure sodium chloride, it's NaCl. Aqueous solution of substance. Now, in order to write a PSI for an aqueous solution of a substance, like a Bronsted-Lowry acid or base, which you did yesterday in discussion class, you simply and flatly have got to know the chemistry which occurs when the solution was prepared. We've talked about some of that already. Aqueous solution of strong Bronsted-Lowry acid. To what extent does the strong Bronsted-Lowry acid react with the solvent in making a solution? Practically speaking, 100%. Which means this solution will inventory as hydronium ion, the conjugate base of the acid, given that you learned conjugate language yesterday, and of course water, the solvent. This is all on the sheet you picked up. You don't have to hurry up and write it down. It's all in the notes, but the sheet's got it much more condensed and I think far better organized. Weak acid. To what extent does a weak acid react with water solvent when the solution of the weak acid is prepared? At least for most cases. small extent. There's exceptions. Let's not worry about the exceptions now. We'll take it as generally small extent. And that will always hold if the original molarity, M sub I, of the weak acid is large, like 10th molar or greater, okay? So the water solution of the weak acid will inventory as the weak acid itself, plus of course solvent water. Now, are there other possible species which might exist in this water solution of the weak acid? What if the weak acid is a salt? Pardon me. What if the source of the weak acid is a salt, like ammonium chloride? If you've got 10th molar ammonium chloride solution, the solution is mildly acidic. 10th molar ammonium chloride solution show you a pH that's about 6, somewhat less than 7. So what's the inventory? Ammonium ion, water of course, but also chloride ion, because the source of that weak acid ammonium ion is the ionic compound ammonium chloride. And we already know when ionic compounds dissolve in water, at the minimum, they always dissociate and put their component ions in solution. Strong base, same idea. Strong base, other than hydroxide ion, reacts with water, extent of 100% to become hydroxide ion. So, the water solution of the strong base will be hydroxide ion, HO minus if you please. The conjugate acid of that strong base, and if the source of the strong base was a salt, like sodium hydroxide, then sodium ion as well. Okay? Weak base. The weak base itself. The conjugate acid of the weak base? No. Just the weak base itself. And water. And if the source of the weak base is an ionic compound, like sodium acetate, then sodium ion. All you got to do is pay attention to the formula of the material from which the solution has been produced, and pay attention to its chemistry. Now at this point you're not going to be familiar with the chemistry of many of these common weak acids and bases. But there's a table of acids and bases in the notes which will allow you to develop familiarity. And next class I'm going to give you a handout again. This will be an information sheet. And on that information sheet, you will see a formula list of all the weak acids and bases with which we shall deal this term. And you won't have to memorize this information, but you'll have to be able to use it. Why not memorize? Because on every quiz and every exam, I will give you the information sheet. I don't expect you to memorize it. I understand in 45 they're having you memorize formulas. Stupid! Your job is to know what these formulas can do for you. People who are asked to memorize this stuff will forget that stuff as soon as they're no longer responsible to spit it back on an exam or quiz. He says, come on now, you're trying to get these people to understand. Their brains are not magnetic tapes. Their brains are marvelous places in which computations occur. Because if you've not yet realized it, the best computer you got by far is this thing, not that damn thing you push buttons on. And a very special weak acid are hydrated metal ions. Again, we're going to talk about this in greater extent next time. But just as a takeoff on what you did yesterday and writing inventories, given that you recognize for water solution, if in water solution you're dealing with an acid stronger than hydronium ion, the inventory for that water solution will always be hydronium ion. and the conjugate base of the reacting acid, because that acid will react with water to an extent which is practically speaking 100%. So you won't find the acid itself in the solution, like 1 molar HCl. You can't find any HCl molecules in there. That's why writing HClAQ is a lie. You're written a formula for something which doesn't exist. That's what the leveling effect is about. So let's imagine that I ask you to consider doing Bronsted-Lowry acid-base chemistry. Chemistry which hinges on the exchange of H+, the hydrogen proton. The reacting acid gives the H+, the reacting base captures the H+. But now you're going to do Bronsted-Lowry acid-base chemistry in pure liquid ammonia, and studies have been done. Pure methanol, studies have been done. And pure methyl hydroxylamine, studies have been done. In pure liquid ammonia, right now on your paper, write the formula for the strongest acid which can exist in high concentration in pure liquid ammonia used as a solvent for Bronsted-Lowry acid-base chemistry. Well, what the leveling effect tells you is that this acid is simply the conjugate acid of the solvent itself, just like in water. The strongest acid you can find at high concentration is hydronium ion, the conjugate acid of water. The strongest base you can ever find at high concentration is hydroxide ion, the conjugate base of water. So here, ammonium ion and the amide ion. This is what you get when you add H+ to this, and this is what you get when you subtract H+ from this. And in each case, the charge is on the nitrogen atom. That's why the formula should be written like this. Now let's look at methanol. For starters, if I'm going to write the formula of the strongest acid which can be found at high concentration in methanol, which means what do I get when I add H+ to this molecule, you've got to make a decision. If H+ reacts with this molecule, where does the H+ land? You think it'll land on one of these non-bonding pairs? Where else could it land? You're going to make a coordinate covalent bond by H+ landing here, creating a positive charge on oxygen. So there is the formula for the conjugate acid of methanol. The acid which in methanol solution will be the strongest acid you can find at high concentration. Now then, let's go back to the parent molecule. How do I write the formula for the conjugate base of this molecule? Now it's a little bit more problematic, because I could subtract one of this H is H+, the oxygen bound H, or one of these three. What do you bet? Well, I'll ask you to think about that. And after you think about that, in preparation for our next gathering, I want you to write the Lewis picture for this molecule, and then write the correct formula for the strongest acid you can find at high concentration in this as solvent, and the strongest base you can find at high concentration in this stuff as solvent. And we'll pick it up from this point.